তোমার জন্য ওই তো ল্যাপটপ আছে তো, খালি কতটা এক্সটেনশন আছে দেখো, এটা একটু খুললে হবে। হ্যাঁ, তাহলে ওখানে আরাম করে বসো, আর কোনো কিছু ইম্পর্টেন্ট হলে আমার একটু, হ্যাঁ আমার একটু খাবার জল দিও। হ্যাঁ আমি রেডি। আমি রেডি। হ্যাঁ হ্যাঁ আমি রেডি। ছবি এলি স্টার্ট করো। হ্যাঁ, ওয়েলকাম টু দি লাইভ সেশন অন ইলেকট্রিক্যাল মেশিনস 1, and I hope you have gone through the course, and in like any course people will have questions, that is most welcome, and several of you have sent some questions to me regarding this course. So, what I have planned, there are so many questions are there, so many means about 30 or so. So, what I will be doing is because the course coverage was mainly on transformer and rotating machines, particularly DC machines. So, I will first try to discuss the questions raised in transformers, then in the rotating machine. So, for example, the first question I should does dot polarity, this is a question sent by one of you, does dot polarity always represents that all the dots would have same polarity irrespective of connection, whether series or isolated? Dot polarity is a property of coupled coils, whether you connect is this way that way, it does not matter. It only indicates that if these two coils are coupled and if you put dot here, it always means that if the voltage polarity at a given instant of time, if this is plus and this voltage is increasing, this side also this will be plus, instantaneous polarity of the voltage will be like that. Another way to interpret the, and once I know that, it will then help me to write down the KVL equations correctly whenever such a mutually coupled coil exists in a circuit. That is the whole idea. And another way of interpreting the dot in case of transformer, in relation to that I must tell that if these two are dot terminals, then we have, I have told you that if current enters through the dot terminals, flux produced will be in the same direction in the core. But in case of transformer, these are one and the various ways of telling about the dots. And another thing is, if these are the two coils, this is dot, then if current you assume to come out from these dot terminals of this coil, then there will be also current in case of a transformer, reflected current in this direction. So, that these two fluxes can oppose and keep the flux where it was earlier. Go through this dot of mutually coupled coils, this concept is very important, particularly while paralleling transformers and in other situations as well. So, that is the thing. Read it, then further we can discuss later. Acha, dots polarity, this is fine. One student has asked that, can you explain with vector diagram what would happen if transformer of different phasor groups are paralleled with example. With example it will not be possible, but the idea is very simple, that is parallel operation of transformer, three phase transformer with different phase groups. That is the question asked, different vector group. We know what vector group is. That is the spirit of the question is this. Suppose you have a transformer whose connection is dy11 and another transformer is there which is dy1. Okay. These are the two possible ways of connecting dy transformer. Can these two transformers be connected in parallel? Assuming that line to line voltage of this side and this sides are same, magnitude, frequency, these are same, whether this is possible to parallel them. See, what happens is this, in case of one transformer, if this is 12, the secondary voltages only I am drawing, these voltages will be like this dy11 and for dy1 it will be like this, this will be dy11. In short, I am telling, I will presume that you have gone through that lecture and then we are trying to answering this question, and this is how, this is dy11, this is dy1, secondary voltage is not. And if this is the secondary of the first transformer A1, B1, C1 and this is A2 second transformer, this superscript means B2 and C2. Now, naturally the line to line voltage existing between A1 B1 and A2 B2, they are not same, their magnitudes are same, but they are phase shifted. So, you cannot connect two sources in parallel when there will be phase shift and balance of voltage, otherwise there will be a short circuit, almost short circuit situation will exist. Therefore, it is forbidden to connect two transformers whose voltage magnitudes are same, frequencies are same, okay, line to line voltage on the secondary, but one belongs to group 11, another belongs to group 1. No, it is not possible. Never try to do that. There will be effectively there will be situation will be like a short circuit. Think about it further, go through my lecture notes, this is one thing. Achha, then another student asked, that is also okay, these questions always often come to our mind. He is asking that why open delta configuration is not considered unbalanced system, as we do not take care of sequence components. Whatever I have understood about this question is this open delta connection. Open delta connection. Open delta connection, as you know, you require only two single phase transformers in order to transform a balanced three phase voltage from one level to another balanced three phase voltage level. Interesting thing is here, when you load the machine with balanced three phase load, both the primary and the secondary currents will be balanced. It is simply because suppose I will just draw sketchily, it is like this is one transformer, its primary and secondaries. Naturally, if you connect the balance load we will consider, if you connect it can be easily shown, and you know that balanced 3 phase voltage exists here. That is why that is the third transformer is removed. Line to line voltage gets fixed by these two voltage only, and that will be 120° apart. So, if you connect a balanced 3 phase load here, here the currents will be balanced, because line to line voltage is balanced, and here is the supply side. Therefore, this current, if this is dot, this current will have reflected component here, this current, if this is dot, it will have reflected current there, and the ratio will be there, and some of these 3 currents will become once again 120° apart. So, line currents on the primary side will be also balanced. This we have explained in our lecture class, please go through it. So, open delta connection, it may, I mean, question may be natural to you, I am not, it is correct to ask that question, that whether a balanced 3 phase load, if you connect here, it will be a balanced 3 phase current on the primary side. The answer is yes, because of the fact the reflected currents of these two, this can be well defined. If these two currents are 120° apart, these two currents, reflected current too will be 120° apart, and their additions or you apply KCL here to get this current, that will be naturally 120° apart. So, please further you convince yourself, that is more important. In short, that is what I want to tell. One student, this question really I really could not understand, but nonetheless I will tell you that generally which type of polarity is preferred, additive or subtractive in transformer, and why. See, it depends upon your applications. For example, you have a transformer which has got 2 secondary coils, and suppose the ratio of this and this is say this is say N 1, this is say N 2, this is say N 3. Okay. Suppose and these are the dots, here, and these dots we can test and decide about. Now, if this is the situation, and if I say that N 1 say voltage per turn, let us calculate voltage per turn. Suppose I say on this side, because I know N 1, I suppose I say it is 4 volt per turns. Mind you, in a transformer this is quite useful to talk about voltage per turn. If you know voltage per turn, what will be the voltage here? If N 2 is say 100, what will be the voltage? It will be 400 volt. Got the point? Voltage per turn is 4. Okay, for a change, let me put it like this. You apply 400 volt here, and suppose this is N 1 is 100, then I get voltage per turn to be 4 volt per turn. Now, suppose I say this turns is 200, N 2 is 200, then how much voltage you will be getting here? 4 into 200, 800 volt, is not? And suppose it is 50 turns, N 3 is equal to, how much voltage you will get here? 200 volt. N 2 is equal to 200, volt per turn is 4. So, 4 into 200 is 800 volt. Similarly, here N 3 is 50. So, you will get 200 volt here. Now, the polarity of the transformer, as I told you, this is dot, this is dot. Now, suppose you from this you want to get 1000 volt. then what you should do? You should connect them in series like this, because minus plus and you will get 1000 volt. It depends. So, whether should I use the add the coil voltages in additive mode or subtractive mode, and the other configuration is also possible, that is 600 volt you can get if you connect it like this. This is 800 volt with this polarity, this is 200 volt with this polarity, then you connect them in this way, and from this 2 you will get 600 volt supply. So, just see, it depends on the use. I think this question is answered. Acha. Now, additive or subtractive polarity I have discussed. Now, somebody has asked about per unit values, we are not discussing. If time permits, at the end I will tell. In transformer, 3 phase winding is there. So, why revolving field is not present? It is a very common Viva type question people will be asking, but the answer to this question is interesting to explore because of the fact that a rotating magnetic field is produced by a balanced 3 phase distributed winding over over the periphery of a cylindrical structure. You have balanced 3 phase distributed winding, which we have discussed at length, and it is because of that the rotating field is produced, is not. But in case of transformer, the coils are concentrated. If you recall that in a transformer, if it is a court type, 3 limb type, the coils are here, coils are on this, only primary I am drawing, say. So, these windings are not distributed in space over 360 degree mechanical degree, not like that. They are concentrated. I mean, these coils are just like coils as we do, not like a winding 180 degree apart, its return coil side is present, not like that. And therefore, if these are excited by 3 phase currents, that is what happens in case of a transformer, they will produce flux which will be like this, and this flux will be 120 degree apart, doing vertically like this and so on. So, no question of any rotating magnetic field will come, because the coils are not distributed, understood. So, in a rotating machine, that was the contribution of, I mean one of the most important contribution of Nikola Tesla. He told that if you have distributed windings, 3 phase machines, excited with 3 phase balanced current, then a rotating magnetic field will result, and based on that you can make a induction machine and also synchronous machine, because armature winding of a synchronous machine is also balanced 3 phase. Anyway, I think this is about that question. One is asking, although this is very, I never tell that any question is bogus, no. Somebody is asking that why transformer rating in KVA is necessary to provide. Any people will say, why you are asking this, this is so obvious. No, it is necessary, how without KVA rating you can, because transformer changes level of voltage from one value to another, that is there. For example, I want to change 200 volt, I want to step down this voltage to 400 volt, and I make a transformer to do that 400 volt, is not. Now, mind you, after all you have using the transformer just not to step up the voltage, but to supply some current, some power to the load. Therefore, eventually you are going to connect some load across the secondary of the transformer, is not, and it will drive current. And the moment you say it is driving current, I must know that value of the current, based on which I will decide about the cross section area of the wires which makes the winding, is not. If somebody says he is going to pass maximum of 10 ampere current here, sorry 10 ampere current here, suppose 400 volt 10 ampere, that is he is going to connect 40 ohm impedance here, then 10 ampere will be the current. And if 10 ampere is the current rating, current you are expecting, maximum current you are expecting, suppose, then you will say that I will make that winding, this winding cross sectional area, this one must be able to carry 10 ampere current, like that you choose, is not. And if it is 10 ampere, this is automatically it will be 20 ampere, we know that, and the cross sectional area of this wire must be double that of this one, because it has to carry 10 ampere and this has to carry 20 ampere. So, instead of telling the current rating, what people have decided that we will specify the voltage ratings of the primary and secondary coil and the KVA rating. So, current is indirectly specified here. Why? Because KVA remains same in a transformer. So, if you know the voltage, you can always calculate what will be the rated current of the respective side, and that is important. Why? Because whoever has designed that transformer, he has kept that current in mind and chosen the wire gauge to make that. I think it has answered your question. KVA rating is very important, okay, apart from voltage rating. Achha, and transformer, what are the other question? What is the condition for proportional load sharing in a transformer with unequal voltages? This thing I have discussed, you can go through, I do not want to do that lengthy derivations. Slight change in voltages, I can always find out the equivalent circuit and find out how much is load is shared. Similarly, same power factor operation with unequal voltage rating, one can work alone, okay. You just go through that. I do not want to write down those equations. Anyway, if personally you have any problems, later you can mail me, I can help you. But for general students, that is not necessary, power factor operation. After all, transformers with which you are connecting in parallel, the change in voltage ratios is allowed, because if the voltage ratios are not perfectly equal, then what happens is this: when the secondary coils are parallel, there will be circulating current, it is to be avoided, and that is why it is not that you allow a lot of variation in the secondary voltages of two transformers and connect them in parallel. Very little voltage variation is allowed. Anyway, this can be discussed along. Achha. Achha, somebody asked, it is actually a design course question, but anyway I will try to briefly discuss this question. He is telling that for what purpose 5-limbed court type structure is used, that is why extra 2-limb for 3-phase transformer. This I will just qualitatively try to tell you, and that much you after knowing that you can consult any design book on a transformer. Now, the idea is like this. See, in case of 3-phase transformers, we 3-phase court type transformer, okay. There are 3 limbs, 3-phase court type transformer. Okay. So, it is like this. So, these are the three limbs on which windings are placed: primary, secondary, Y phase, B phase, R Y B phase. Now, in these transformers, which is 3 limb and 5 limb means 2 additional limbs are will be connected in the core of the transformer. Now, in this transformer, to begin with, I mean very simply, suppose these are the coils, say primary coils only I am drawing, secondary I am not drawing. These are the primary coils of A, B and C phase like this, like this. Suppose you apply balanced 3 phase voltage across this, listen to me carefully what I am trying to tell, balanced 3 phase voltage across it. Now, what happens in a coil which is on a iron core, the flux level, recall that flux is decided by the supply voltage and frequency and supply frequency. This is a very, always remember that frequency, because see V is approximately for any phase, it is to RMS value will be on the primary side 4.44 A phi max N 1 etcetera. So, phi max gets decided the moment you have decided this other things will be constant. So, this is the situation, it is proportional to V 1 by F. Therefore, it looks like that flux in this limb, maximum value of the flux, they will be 120 degree phase apart for A, B, C phase, no doubt, but it is 120 degree apart these fluxes. And it is this flux which will decide the magnetizing current of a transformer. I am trying to answer this question from the no load current point of view. Okay. Just to give you a feel of this one. Now, this flux is suppose phi A, this flux is phi B and this flux is phi C, A B C phase current. Magnetizing current is flowing, secondary I have not connected anything, just to understand what is happening. Now, the question is the maximum value of the flux is decided by V 1 by F for each one of them. Now, the magnetizing current which is needed to establish this flux, then I told you you have to go to the BH curve of the transformer and for this phi find out what is the magnetizing current. Or you can say that this flux, how this flux will return, this flux it will return via these two paths. Similarly, this flux will return via these two paths phi B. Phi B will be divided into 2, it will move like this, phi C once again will be doing like that. Therefore, the reluctance seen by the MMF which is producing phi A. So, phi A will be, I mean to tell you slightly in detail, it is like this. This is the thing. Suppose you consider phi A. What is the this phi A is produced, okay, and phi A then divides into two paths. How flux will be shared between these two portions is decided by the reluctance of the path, is not phi A reluctance of the path. Suppose you say reluctance of say so MMF by reluctance is flux MMF I mean telling it reluctance is flux, that is true. Now, the reluctance seen by phi a is decided by whom? This reluctance, suppose this to this reluctance is r, this to this reluctance is r. I mean, I am telling you trying to tell you very simply. Here is reluctance. Suppose let us assume all these reluctances are same, here to here, here to here, here to here. Similarly, here is reluctance for this path, and for this path there is another reluctance, and this first another is this reluctance. Got the point? Then I can find out the equivalent reluctance which this MMF is produced. Find out series parallel method, whatever you do. Similarly, for this coil it will see the same reluctance. So, okay. But for this coil, if you draw this diagram and try to find out and assume very simple case, all the reluctances of these paths are same, you will find reluctances are different. In fact, reluctance seen by this coil will be less. Therefore, magnetizing current drawn by A, B, C phase will be not balanced. People do not mind that. Okay, this is after all magnetizing current which is less. I have chosen very good magnetic material, and 3-core transformer are very simple, it will occupy less space. You compromise with that, it is accepted, nothing like that. But in 5-limb transformer, what you do, if you have enough money for very big transformer, maybe they will be doing, you can do it like this. You can do it in this way. Oh, sorry, so I will draw it like this 1, 2, 3, okay. And this is the thing, and here is the thing. How many limbs? 1, 2, 3. 1, 2, 3, 4, 5 limbs you just connect, and you imagine that here you have this primary coil, and this coil will have nice return path through this only, like a single phase transformer. Similarly, this fellow will have this path, and this one will have these two paths. These other reluctances will not matter much. Therefore, you can make the reluctance to appear same for all the coils and making the magnetizing current same. Apart from that, people say that in case of some fault in the transformer, zero sequence or say third harmonic flux or zero sequence flux will be produced, and in this case they will have no return path, because zero sequence component of unbalanced fluxes means what? They will simultaneously changing with time. So, what will be their return path? In case of 3-limb transformer, what happens? This third harmonic fluxes, if at all any, because of magnetizing current problem or because of some unbalanced current flowing on the secondary side, positive, negative and zero sequence component will be there. Zero sequences are cophasal. So, they will produce flux like this, simultaneously trying to increase, decreasing like that, and those fluxes will force their way through the tank, coil, etc. That way they will manage to find their path, and therefore, causing extra losses in the tank surface, which is made of iron of a transformer like that. So, those things also can be avoided in such a situations, because third harmonic flux will find their way also through the core. That is as if these are different primary, secondary. It has nice path here, this phase, this like that. You think in that way, although this was not part of the course 5 limbed transformer. It is a special thing about the design course. When you read rightly for exam, better do not concentrate upon, although the questions have come to your mind, you have read something that is very encouraging, no doubt. But for this course this need not be, maybe at later level of machine 2 course you can discuss about that. But nonetheless, I thought I will tell you something about that, because the question has come to your mind. This question I really could not understand, how belt harmonics are suppressed. Is it third harmonic? Not sure, most probably third harmonic you meant. Somebody has written that I am not able to feel no load current in a transformer. Sir, I think it should be very high, as voltage applied to primary winding, which is limited by winding impedance only. Sir, help me to. Anyway, since he is, once again I am telling, it is good you have asked this question, and look at this equation. Say, see, suppose you have you are having a transformer like this, because it looks like he has a very fundamental question which if he does not understand, he cannot proceed further. That is why I am telling him. Look here, if you apply a voltage, certain voltage with frequency, the flux level in the core gets fixed, as I told you, flux level, and how much current it will draw. Forget about impedances from the circuit point of view, that we will discuss later, but what I am telling, it is a magnetic circuit. This much flux core has to produce, then how much current it is drawing. The answer to this question is, you go to the BH curve of this material. So, I can calculate B max from phi max by this cross sectional area A, and BH curve of the material suppose is like this. I am not showing the hysteresis loop to simplify the matter. So, this is your B and this is your H, flux density curve. Then you say that okay, core has produced B max. To produce this B max, how much current is necessary? So, go to B max, this I explained at length most probably in my lecture class, and from this you find out what is the value of H, and this will be equal to N into magnetizing current by L. L is the physical length of the flux path, N is the number of turns, etc., and you can calculate the current. Whatever current will be there, that is the current to establish the flux. So, to establish, and if you use a better and better material, the current necessary to establish this flux will be less, this much and this much. Got the point. So, this is how it will be like that. So, current needed can be made vanishingly small if you use better and better material, clear. Therefore, after you find that current, then I am telling you blindly that you know the applied voltage, you know how much current it is drawing. Therefore, you do V I by and you will get the value of Z, which will be quite high. When the transformer secondary is open circuited, you apply rated voltage frequency, the current drawn will be very little. If with this one open circuited and you apply a known voltage, the current drawn will be less and this coil will see large impedance, not a low impedance. And if it shows low impedance, that means it is a very badly designed transformer. Got the point? So, I think we have done like that. Then maybe as an annexure, Rahul Gupta has added, because it is in this line, I will tell you something, that is Rahul Gupta is asking that I cannot understand the physical meaning of magnetizing current. So, I think you have understood what is the physical meaning of magnetizing current. The current needed to establish the flux. Who decides the flux? See, in case of DC magnetic circuit, what you do? It is like this. You have number of turns, you pass any current you like to pass. So, Ni is known, and then you go to BH curve of the material, H is known, it is other way around you do to find out the B. But in case of transformer, it is just opposite. You apply a voltage at a certain frequency, your phi max gets fixed, and then current is decided. It is not in your hand, what I am telling. What is in your hand is, okay, how much B max I will allow. You play, because this equation, if you see, it is V 1 by 4.44 F N 1 etcetera, like this, 4.44 by F N 1 etcetera. So, flux gets decided, and to produce this much phi max, how much maximum value of magnetizing current will be necessary? That current is called magnetizing current. I think I have this is the physical meaning of magnetizing current, Rahul Gupta. You have also asked, that is of course pertinent question, I will not avoid that question, that why you assume BH curve in your initial lecture, not BH loop, which is actually happened in a transformer. He is asking that why not you start with BH loop in a transformer while explaining this thing. Okay, in a transformer, I will this is the thing actually. The area under the BH curve is very little to reduce the hysteresis loss in a transformer. If somebody has designed a transformer with very big BH loop, it is a very bad transformer, okay, because hysteresis loss will be higher. Now, why people just tell this will be close to B max on the basis that, okay, hysteresis loss is very little, and to get the to understand the transformer, its fundamental operating principles, why you go to that third harmonic effect. What will happen here is if this is the sinusoidal flux, it will be created as I told you, and to create that sinusoidal flux, if the flux is this also we explained, is not we explained this. If this is sinusoidal flux, the current needed I can find out which will not be sinusoidal, which will be slightly distorted like this, but periodic no doubt, slightly it will be distorted. And this current I can always analyze into Fourier component, which will have a fundamental component and a strong, I mean next major component is third harmonic component of flux will be produced. So, remember, as if we have analyzed the transformer, neglected the third harmonic component, which will be less after all 1/3 etcetera, and the established everything at fundamental frequency what is happening. That was the reason why we do not start with a hysteresis loop unnecessarily, unless you want to go further deep into that third harmonic current. In fact, it becomes important in case of 3-phase transformer connections, as you know, star delta connections. Anyway, so enough of this BH curve and third harmonic component. Acha, another question has been asked, Shweta Gupta. She has asked why you can't discuss third harmonic lecture in single phase transformer. I really could not get this question. He is most probably asking that why not in single phase transformer. Okay, something most probably, if I have understood correctly, suppose single phase transformer is there and I have applied a single phase sinusoidal voltage source. If you have applied a single phase sinusoidal voltage source, the moment you do that, in the core a sinusoidal flux has to be developed, and to establish a sinusoidal flux you require a third harmonic component of the current present also, is not. So, how this is explained is somewhat subjective. Anyway, it is interesting to note that. Assume that supply voltage is sinusoidal, flux in the core has to be sinusoidal, because it has to balance this voltage, and if flux in the core is sinusoidal, then the current must have a third harmonic component, but who will supply this third harmonic component of the current to make the flux more sinusoidal? Perhaps that is the question most probably Shweta Gupta has asked. It is like this. Let us assume that this source can supply only sinusoidal current, is not. 50 hertz sinusoidal source can only supply sinusoidal current. So, if it supplies sinusoidal current, other way around, that is, if a coil is excited by single sinusoidal frequency current, then the flux in the core will not be fundamental 50 hertz alone. Induced voltage then will have a prominent third harmonic, opposite thing, and that induced voltage will then find a closed path here and will try to compensate for the third harmonic current which is necessary to make the flux more like sinusoidal. Got the point? Remember that if you assume the flux to be sinusoidal, you must ensure the current in the line, in the winding, must contain a third harmonic component. Is that clear? And if you say that flux in the core is not sinusoidal, because current if the current in the line is fundamental 50 hertz, then flux cannot be just fundamental component alone, there will be third harmonic component. But that third harmonic component itself will try to pass that necessary third harmonic current in this coil in order to suppress the third harmonic voltage. I do not know because time is running out, there is another session. I thought some rotating machine question. What can I do? Can you, because that will require some time. For example, many of you have asked, told me that brush shift of synchronous DC motor with whatever little time I have, I think I will not be. I thought I will, but in between some questions came. Can you please go through those lectures once again? Only I will tell you this much, that in a DC machine, because 1-2 fellows have asked, this is your north pole and this is south pole. Suppose I am not showing the winding diagram, and suppose it is acting as a generator, it is moving like this in this direction. This is the direction of rotation, who is making it rotate? Prime mover. So, this is the direction of rotation of this generator, and under no load condition there is absolutely no problem. There will be no flux in this axis. Okay? The flux distribution will be like this, and that is why it is called interpolar zone. No flux, 0 flux, when the machine is not armature is not carrying any current. But the moment armature carries current and assuming it to be generator, what pole these two will produce, south or north? Because after all it is the interactions between two sets of magnet, whether should it be north NR, this is suppose NSSS stator, whether should it be NR SR or SR NR. Since prime mover torque is in this direction, I can find out right hand rule, find out the current, etc. Okay, let me do that, that is much easier to follow. So, what will be the direction of the current? This will be cross and this will be dot. So, armature this will become SR and this will become NR, is not, lines of force will come out. Therefore, you see now in the quadrature axis, now some lines of force in this direction has been created, and north pole also create like this. Therefore, in this position now it is not 0, there is some, it gets distorted, there is some flux exist here. Therefore, how to nullify this flux? You can put some interpole on this axis, you can put and can nullify that work. So, 0 of this flux goes to rights here, somewhere here, I do not know where. So, sometimes people what they do, they will make a slight brush shift here. The question was asked, how do you know where it is 0? Yes, it will not, but it will improve commutation, because 0 will take place here. What I am telling is this, here it is certainly not 0, current distribution will be like this, this is all cross here and these are all dots here, current distribution will be like this. But one thing I am sure about, here a flux is produced in this direction and the 0 will be here. So, give a shift there. Mind you, this conductor has already come under the purview of south pole. So, it is getting trained how to behave under south pole. So, I will stop here, and if further questions are there, please mail me, I will try best to answer that. Thank you so much for cooperating.